By the early morning of March 15, 2026, astronomers were exhausted. They had spent months engaged in a grueling hunt for 3I Atlas, a confirmed interstellar object passing through our solar system. The math told them exactly where to look next. Orbital predictions pointed to a precise set of coordinates near Jupiter, prompting observers to train the Canary One telescope directly at the Jovian system. This image shows what the models predicted. Deep in the star field, where the red arrow points, the telescope captured a signal, but it is incredibly weak. In the raw data, it's a tiny cluster of pixels registering barely above the camera's baseline electronic noise. We are left with a difficult question. Are we actually looking at the last visible trace of an interstellar visitor, or is this just random sensor noise that happens to fulfill our expectations? To figure out if an object is real and not just a camera artifact, astronomers analyze tracking data over time to see how it moves. These raw images capture the space immediately surrounding Jupiter. On the left side, taken March 14th, you see a distinct target circled in red. 24 hours later, capturing the exact same region, the target has shifted to the complete opposite side of the frame. An orbiting physical body would behave exactly like this. For example, a Jovian moon like Io has an orbital period of about 42.5 hours. If you wait a full day, it will travel to the opposite side of the planet while maintaining a consistent distance. However, the environment around Jupiter is highly chaotic. Intense glare and extreme radiation from the giant planet frequently strike camera sensors, creating temporary hot pixels that masquerade as real objects. The object's position strongly suggests an orbit, but in a neighborhood this flooded with radiation, positional data is simply not enough to confirm that we found 3I Atlas. We have to move past where the object is and examine the actual structure of the light hitting the camera. This image displays a highly magnified view of the target from the March 14th observation. The false colors represent the raw intensity of the photons hitting the sensor. In this initial capture, the light clusters tightly in the center, creating the illusion of a solid, structured mass. But look at the data collected 24 hours later. The visual shape of the light distribution completely changes, appearing much dimmer and fracturing into a blocky, unfamiliar pattern. At this extreme level of magnification, an instrument is only collecting a few thousand photons per pixel. Random energetic noise dances and shifts across the digital sensor, easily mimicking the geometry of a physical body. Relying on visual shape at the absolute limit is deeply flawed. To prove 3I Atlas, we have to stop looking at the object itself and look for its impact on the surrounding environment. This leads to the final definitive test. If a massive interstellar body flew past Jupiter, we could detect its gravitational wake or see alterations in the planet's atmospheric signature. This chart shows a baseline spectroscopic reading of Jupiter taken January 21st, revealing the exact chemical makeup of its atmosphere. Overlaying the new spectrum data captured on March 15th, the methane absorption bands line up perfectly with the baseline. There is absolutely no deviation. The interstellar visitor left zero measurable trace or impact on the Jovian system. The investigation leaves us with conflicting realities. The signal appeared exactly where orbital mechanics predicted, but the chaotic light profile and the completely undisturbed Jovian atmosphere cast a heavy shadow of doubt on its actual physical existence. This view captures Jupiter on the left, and across the vast scale of space, a tiny, ambiguous blip marked by a red arrow on the right. At the very edge of our technological limits, the line between discovery and an illusion is incredibly thin. We expect to see something remarkable in the dark, and sometimes that human expectation is the only thing we successfully capture.